Alright, what's up, you guys? So, I haven't even edited the last episode, but my most recent upload was the uh, 4 principles or concepts of human behavior, and I just really enjoyed the whole couch angle. I enjoyed it so much that I realized I needed a little bit of an extension on my tripod to hold the receiver for this wireless microphone, and I figured I would get a magnetic clip so that way I can more optimally place this bad boy here. And yeah, so I filmed the last episode, which was section 85, and I probably looked horrible. I was wearing the some of you may think it's goofy, but the whole red light glasses, I'm probably going to slap those on mid episode here. And I had the whole David Foster Wallace "This Is Water" bandana going. And anyways, I figured this is kind of like a reading before going to bed vibe. You know what I mean? That's kind of what's at the core of this whole couch angle, I think. So, along with that, I'm going to read section 86, even though I haven't even uploaded section 85 yet. Obviously, by the time you're watching this, it's already come out, but I'm also going to probably mid episode today go and microwave myself a nice glass of whole milk and have some Oreos in the true spirit of reading before going to bed. So it's also shortly before 6 p.m. as of filming this, so my cat, my son, the love of my life, is going to be eating his dinner here. Wow. Just as I said that, did you hear that? That's his food. I'm not going to edit that out. What a better way to start this? Section 86. Developable surfaces as envelopes of families of planes. We will now apply the results obtained in the preceding section to the important particular case of one-parameter families of planes. Such a family can be represented in the form where we have a function capital G in terms of a vector x and then a scalar parameter t. And this function capital G is equal to the scalar product between the vector a in terms of t with then the vector x. So it's the scalar product of vector a with vector x, then plus the function lowercase c, which is in terms of t. This equals 0, where this vector a in terms of t is a unit vector normal to the corresponding plane. If dA dt, which is equivalent to a prime, is equivalent to 0, the 0 vector, then the family consists of parallel planes and does not have an envelope. We will exclude this case from our further investigation and even assume that a prime is non-zero or is not the 0 vector for all values of t. From the relation above for the function capital G equals 0, we obtained that partial g partial t is equal to the scalar product of vector a prime with vector x, then plus c prime, which is equal to 0, and partial squared g partial t squared equals the scalar product of vector a double prime with the vector x, and then plus c double prime, which equals 0, where primes denote derivatives with respect to t. In consequence of the results obtained in the preceding section, the characteristics of the family given by g equals 0 are the intersections of the planes defined by the relation scalar product of a with x plus c equals 0 and the relation for partial g partial t equals 0, namely the scalar product of a prime with x then plus c prime equals 0. These are straight lines. If the determinant capital D, which equals the determinant then of the 3, I guess you could say, column vectors a prime, and a double prime, if this determinant does not vanish identically, then the system of equations given by g equals 0, partial g partial t equals 0, and partial squared g partial t squared equals 0 has a solution. Say the vector x equals the vector function h in terms of t. If this is a curve, it is the edge of regression of the envelope of the family given by or implied by the representation of the function capital G in terms of the vector x and the scalar t being equal to 0. The function g being equal to 0, that is. In consequence of theorems 85.1 and 85.2, the envelope is the tangent surface of this edge of regression. If, however, h of t, let's say that that's h naught, is then a constant, then by the governing relation for this family of planes that we're considering here, we have that the scalar product of the vector a with the vector h naught then plus c equals 0. That is, every plane of the family given by the governing relation in this section passes through the point h naught. Consequently, in this particular case, the envelope is a cone with apex at h naught, or if the planes of the family given by the governing g equals 0 relation of this entire section have a straight line in common, the envelope degenerates into this straight line. In this degenerate case, the planes form a pencil and all characteristics coincide. Hence, the line of intersection of all planes given by g equals 0 with the plane partial g partial t equals 0 must be independent of t and must therefore be identical with the straight line defined by partial g partial t equals 0 and partial squared g partial t squared equals 0. This case occurs if and only if the rank of the matrix, which is a 3 by 4 matrix, and we're going to denote it as capital M. I'm going to read it off here entry-wise, column-wise, that is. So starting in the first column, we have A1, A1 prime, and then A1 double prime. Second column, A2, A2 prime, A2 double prime. Third column, A3, A3 prime, and then A3 double prime. And then in the fourth and final column, we have C, C prime, and C double prime. So this degenerate case where the planes form a pencil and all characteristics coincide occurs if and only if the rank of this matrix, capital M, is less than 3. If the rank of capital M is equal to 3, and that determinant capital D is equal to 0, we obtain a cylinder as envelope. This can be proved as follows. The determinant capital D vanishes if and only if the vectors A prime, and A double prime are linearly dependent, that is, lie in the same plane. We denote by M the unit normal vector to this plane. Then, if capital D equals 0, that determinant is 0, then we have three cases. First case A, we have the scalar product of M and A is equal to 0. Second case, the scalar product of M and A prime is equal to 0. And in the third case, scalar product of M and A double prime is equal to 0. Now, if we differentiate the first case, then in consequence of the second case, we find that the scalar product of M prime with A is equal to 0. And if we differentiate the scalar product of M with A prime being equal to 0, then in consequence of the scalar product of M with A double prime being equal to 0, we have that the scalar product of M prime with A prime is equal to 0. And then from the scalar product of M and A being 0, and from the scalar product of M prime and A being 0, we see that A is orthogonal to M as well as to M prime. And then from the scalar product of M and A prime being 0 and the scalar product of M prime and A prime being 0, it follows that the same is true with respect to A prime, namely A prime is orthogonal to M as well as to M prime. Since M is a unit vector, M prime cannot be parallel to M. In order that the equations for the scalar product of M with A prime, and A double prime respectively, the consequent scalar products of M prime with A and A prime, in order that these equations be consistent, M prime equals 0 must be true. That is, M which equals M naught is a constant. Hence, by the scalar product of M and A being 0, for all values of t, the normal vector A to the planes given by the governing relation for this section, function capital G in terms of vector x and scalar t is then equal to 0, is orthogonal to the constant vector M naught. This means that the planes given by G equals 0 and consequently their characteristics also are parallel to M naught. From this we obtain the statement that if the rank of capital M, that 3 by 4 matrix, is equal to 3 and capital D equals 0, the envelope of function capital G equals 0, in this case, is a cylinder. We sum up our results as follows. Theorem 86.1. If the envelope of a one-parameter family of planes is a surface, then it is always a developable one. Furthermore, we have theorem 86.2. If the planes of the family given by the function capital G equals 0, as I've said many times throughout this now, are not parallel, if there does not exist a point common to all planes, and if that determinant capital D is non-zero, for which refer to the vector x being equal to the vector valued function h in terms of t, then the envelope of this family is a tangent surface, namely the tangent surface of its edge of regression. And that's the end of section 86. So I think 13 minutes so far, but as promised, let's do this. Got the creatine. This is probably going to be the last of the milk. Oh boy. What do I always say about this lighting? It's like the lifting, as I also have been saying, has not been going well. It's like the last year, but still, it's like I just look shredded under these kitchen lights. Okay. That's probably enough. Oh, yeah. Brothers. You know what it is. Oreo time. Just gonna... Nice. Oh, I have to cherish that because that's the last of the milk. I'm not gonna go to the store today because I'm obviously getting ready to go to bed. Cookies and milk, reading a book. What do you think this is? Oh man. This is my bad side. It's not as good. My right side's better, in my opinion. It's almost too good. Wow. I'm at a point where it's like one more Oreo would be too much. But this is like the perfect last amount of milk, you know? We can't have it all. We can never truly have perfection, you know? Also, I'm going to say shout out to this. You may say at first glance, oh, that's just a normal Rubik's Cube, but it's not. It's a blind cube, not for blindfolded solving, but its closest formally used term, if you will, would be a Braille cube, where instead of colors on a Rubik's Cube, an individual color would be represented with an individual Braille symbol. But honestly, I tried doing that back in the day, where like I tried finding like some Braille stick-on little dots. That didn't work. You could use like a lighter and a paper clip and, you know, melt the plastic. That just was, you know, crude, and I didn't actually want to do that. But that's like what I heard, believe it or not, Dan Knights say back in the day, because I asked him personally when I heard about a rumor from, you know, some like ancient YouTube video that I saw him give an interview on and talk about it back in the day, being like, "Oh, I had a Braille cube," and so then when I was like a 13-year-old, I went and found him at a Rubik's cube competition, and I'm like, "Hey, Dan Knights, how do you?" Anyways, but the point being is that this one, like you can see, the white has these like bullseyes with the raised outer perimeter. Then there's like these circular, just kind of smooth, raised ones. There's these stars. There's a flat side. These are like some stars, some hearts. Then these raised squares. Yeah, first couple of solves, just like not looking at it, but just by touching it to feel which pieces are what. It's been very fun. As someone who's done every single cube under the sun, essentially, from probably 99.99% of the people watching this is perspective. I've done every cube under the sun. Whether I'm fast or good at it or can remember the solution off the top of my head for all of them is another thing, but this one's been fun. Anyways, here we go. Let's do this. There's like 3 problem proofs, but we're going to crank them out. Section 87, envelope of the osculating normal and rectifying planes of a curved polar surface. As was shown in section 19, all the way back in chapter 2, which is on contact and the osculating sphere. I remember now because that was like the first section in the book that was like beefy theorems and proofs. Yeah, 4 theorems. There were 3 out of 4 of them had proofs, I'm pretty sure, in there. And then 3 problems. One's investigate blank. Next one, proof. Next one, determine the conditions. So that's like Welcome to Differential Geometry by Erwin Kreisig. Okay, that was section 19. So as was shown back in section 19 on contact and the osculating sphere, there was also, I remember, Vanderhagen the Stampede comment where it was like trying to clarify the definition of contact, like the order of contact, equating what order of partial derivatives at a point. Anywho, as was shown in section 19, to every point of a curve with a vector parametric representation y in terms of arc length lowercase s with non-vanishing curvature kappa, we can associate a polar axis. The polar axis can be represented in the form which is a vector parametrized by t, and so we have x of t equals vector y plus scalar rho times vector p plus scalar t times vector b, where kappa is greater than 0. And for this we can refer back to section 19, expression 10. The position vectors of the centers of osculating spheres is of the form vector A equals vector x plus rho times vector p plus beta times vector b. And these are, again, to remind ourselves, T, P, and B is a Frenet frame. T for tangent, P for principal normal, B for binormal. T cross P equals B. Moving on, where rho equals 1 over kappa is the radius of curvature of y of s. So that's another reminder, is a definition of curvature is just the reciprocal of the radius of osculating circles or osculating spheres. Vectors p and b are the unit principal and unit binormal vectors. What did I just say? And the real variable t is the parameter of the representation x of t equals y plus rho times p plus t times b. The polar axis is the locus of the centers of the spheres which have a contact of second order, at least, with vector y of s at the corresponding point. Furthermore, we found that, in general, to every point of y of s there is exactly one sphere which has a contact of third order with y of s at that point. The center of this sphere has the position vector x equal to the vector y plus rho times the vector p plus rho dot over tau then times the vector b, where kappa is greater than 0 and tau is non-zero. Remember, tau is torsion. What the fuck is torsion? In general, the polar axes of a curve generate a surface which is called the polar surface of this curve. In consequence of the representation of the polar axis, which was read earlier, the polar surface of a curve y of s can be represented in the form vector x in terms of s and t equals vector y in terms of s plus rho in terms of s, then times vector p in terms of s plus t, then times vector b in terms of s, where kappa is greater than 0. The arc length lowercase s of the vector y in terms of lowercase s and the parameter t are the coordinates on this surface. We come to an example. The polar surface of a plane curve is a cylinder because the unit binormal vector of such a curve is constant. The polar surface of a spherical curve, for which refer back to problem 19.3, is a cone with apex at the center of the sphere on which the curve lies. The polars of a circle coincide. They are orthogonal to the plane of the circle and pass through its center. Hence, these polars do not generate a surface. And now we come to theorem 87.1. The envelope capital E of the normal planes to a curve capital C of class r greater than or equal to 2 with positive curvature kappa is identical with the polar surface of this curve. If capital C is of class r star greater than or equal to 3, and if its torsion tau does not vanish, then the envelope capital E has an edge of regression capital R, and capital R is the locus of the centers of the osculating spheres of the curve capital C. The proof is as follows. Let vector t of s, vector p of s, and vector b of s be the vectors of the moving trihedron of the curve capital C with a vector parametric representation y in terms of lowercase s, that is to say, arc length. The normal planes to the curve capital C are orthogonal to the unit tangent vector t of s. Hence, we can represent the family of these planes in the form function capital G in terms of vector x and s being thus equal to the scalar product of, first we have vector x minus vector y of s. So the result of that difference then is scalar product with vector t of s, which is equal then to 0. And we can refer back to, from section 13, the definitions for the normal plane, the rectifying plane, and the osculating plane. So for here specifically, we can refer back to section 13 for the definition of the normal plane. Quantity vector z minus vector x, then scalar product with t is equal to 0. By means of the formulae of Frenet, we find that partial g partial s is equal to negative of the scalar product of t with itself, then minus, we take the vector x minus the vector y, then scalar product with kappa times the vector p. This is all equal to 0, or since the scalar product of t with itself is equal to 1, and kappa equals 1 over rho, which is then greater than 0, the scalar product of vector x minus vector y then with vector p is equal to rho. In consequence of, from the beginning of this proof, capital G equals 0, we can represent the vector which is the result of taking vector x minus vector y in the form x minus y equals lowercase q times vector p plus t times vector b. Inserting this relation into the previous relation, which is x minus y scalar product with p equals rho, we find that q equals rho. Consequently, what I just read where we have x minus y equals q times vector p plus t times vector b, that becomes identical with the representation of a polar axis from the beginning of the section. Hence, the characteristics of the family of the normal planes to the curve capital C are the polar axes of that curve, and the envelope of the family under consideration is identical with the polar surface of that curve. In order to determine the edge of regression of the envelope, we differentiate the x minus y scalar product with vector p equals rho relation with respect to s. So we have the negative of the scalar product of t with p, each both being vectors of course, then plus taking vector x minus vector y and then scalar product that result with vector p dot, then that equals rho dot altogether. In consequence of the function capital G equals 0 from the beginning of this proof, and from section 86, as we remember, from before the cookies, in consequence of that and the formulae of Frenet, and scalar product of the tangent vector with the principal normal vector, both being unit vectors in this case, being equal to 0, we obtain from this relation take the difference, vector x minus vector y, and then scalar product that with tau times vector b. That equals rho dot. And if we insert the representation of a polar surface from expression 87.1 prime towards the beginning of the section, inserting that into what I just read and taking scalar product of vector p with vector b equals 0 and the scalar product of vector b with itself being 1 into account, we have that t equals rho dot over tau, where tau is non-zero. When inserting this, the expression 87.1 prime from towards the beginning of this section thus takes the form of expression 87.2. Hence, the edge of regression of the envelope of the normal planes of the curve capital C is the locus of the centers of the osculating spheres of capital C. We may also formulate the second statement of theorem 87.1 in the following manner. The polar surface of a curve capital C is the tangent surface of the curve generated by the centers of the osculating spheres of capital C. By comparing expressions 87.1 prime and 22.3, what is 22.3? From the involutes and evolutes section, we have 22.3 is vector y in terms of s, arc length, is equal to vector x in terms of s plus rho in terms of s, then times this quantity, vector p of s plus vector b of s, then times the cotangent of alpha of s, where alpha of s is equal to the integral from 0 to s of tau of sigma d sigma plus lowercase k star. And it says here, each value of the constant lowercase k star corresponds to exactly one of the infinite many evolutes of the curve capital C. So we're bringing it all back, and when we compare that to 87.1 prime now, we see that the evolutes of a curve lie on its polar surface. Through every point of this surface, there passes one and only one evolute. By similar considerations of the envelopes of the osculating planes and of the rectifying planes, we obtain the following results. Theorem 87.2. The envelope of the osculating planes of a curve of class r greater than or equal to 3 with non-vanishing curvature and torsion is identical with the tangent surface of this curve. Theorem 87.3. Every generator of the envelope of the rectifying planes of a curve of class r greater than or equal to 3 with non-vanishing curvature passes through a point of the curve and has the direction of the corresponding vector of Darboux. The envelope of the rectifying planes of a curve is known as its rectifying developable surface. This name is justified by the following fact. If this surface is bent into a plane, the curve becomes a straight line, that is quote, rectified, unquote. And now we come to the three problems at the end of section 87, which is where we will leave off today. Problem 87.1. Prove theorem 87.2. The solution, or the proof rather, is as follows. Since the unit binormal vector b to the curve, which has a vector parametric representation y in terms of s, is orthogonal to the osculating plane, the family of those planes can be represented in the form of a function capital G in terms of the vector x and arc length lowercase s, which is equal to the scalar product of vector x minus vector y of s, then taking the result of that and taking the scalar product with vector b in terms of s, and in all, function capital G is equal to 0. Here, of course, s denotes the arc length of vector y of s. In consequence of the definition for the characteristic of a surface with respect to its corresponding family of surfaces, the characteristics of the family can be represented by what I just read, the function capital G being equal to 0, and partial G partial s is then equal to the negative of the scalar product of t with b, then plus taking vector x minus vector y, then scalar product with vector b dot. In all, this is equal to 0, or since tau is non-zero, we have vector x minus vector y, then scalar product with vector p is equal to 0. It follows from this, as well as from the initial capital G equals 0, that the vector, which is the result of taking vector x minus vector y, is orthogonal to vector b, the binormal, as well as to the unit principal normal vector p, that is, x minus y lies in the tangent to vector y of s, and vector x in terms of s and t is equal to vector y of s plus parameter t then times vector t tangent in terms of S. This is a representation of the envelope of the osculating planes. The formula for x in terms of S and t that I just read, and expression 58.1, which is just the representation for a ruled surface, vector x in terms of S and t is equal to vector y in terms of S plus scalar t, then times vector z in terms of S, where vector y dot cross product with vector z is not equal to the 0 vector. Continuing on, the tangent surface of a curve is the envelope of the family of the osculating planes. If we differentiate the previously read scalar product of x minus y with p being equal to 0 with respect to arc length, we find the negative of the scalar product of vector t with a vector p, then plus, taking the result of vector x minus vector y and taking the scalar product with vector p dot, this in all is equal to 0. From the initial capital G function equals 0, from kappa being greater than 0, and from the formulae of Frenet, we have that if we take the results of vector x minus vector y and scalar product that with the tangent vector t, that is equal to 0. Hence, because of this ruled developable surface looking relation, which is the third expression in this solution or proof, vector x is equal to vector y. That is, the curve which is given by vector y in terms of S is the edge of regression of the envelope of the osculating planes. Moving right along, problem 87.2 is prove theorem 87.3. The proof is as follows. The family of the rectifying planes of a curve, y of S, can be represented in the form of a function capital G in terms of vector x and S arc length, which is equal to taking the vector x minus the vector y in terms of S, and taking the result and taking the scalar product with the vector p of S, where p is the unit principal normal vector, and in all, the function capital G is equal to 0. And again, we can refer back to section 13, which explicitly gives the definition for a rectifying plane. Take the vector z minus the vector x, take the result, and take the scalar product with the unit principal normal vector p. Everywhere that that's equal to 0, that's the rectifying plane, and of course, we need to have positive curvature. So, as per usual, lowercase s denotes the arc length of this vector y, which is in terms of that lowercase s. Consequently, the vector x minus y is of the form x minus y equals alpha times vector t plus beta times vector b. According to the definition for the characteristic of an envelope of a family of surfaces, the characteristics of the family, which we're talking about in this problem, which is the proof of theorem 87.3, can be represented by that function capital G in terms of x and s being equal to 0. And partial G partial s is equal to the negative of the scalar product of vector t with the vector p plus then x minus y scalar product with a vector p dot, in all being equal to 0, or because of the formulae of Frenet, take the result of taking vector x minus vector y and then scalar product that with negative kappa times vector t plus tau times vector b. This is all equal to 0. And if we insert into this the previously read relation for x minus y, we find that we have negative alpha times kappa plus beta times tau is equal to 0, or alpha equals c times tau and beta equals c times kappa, where c is a constant. Consequently, vector x minus vector y is equal to c times the quantity tau times vector t plus kappa times vector b, which is equal to then c times vector d, where, wow, this is crazy. Wow, this is insane here. Where the vector d is the vector of Darboux. Wow, you would never have thought that the vector of Darboux would ever show up again. You would have just thought it really is like Chekhov's rifle, where, to be honest with you, I was reading the Theory of Curves chapter the first time through. That was over a year ago. And I'm thinking to myself, this vector of Darboux, when is this ever going to come up again? It's kind of like the equation of Lancret. Where is it? I'm going to find this. Okay, here we are. This is from section 16, the vector of Darboux, d equals tau times t, tangent vector, plus kappa times b, binormal vector. Wow. Here we are, section 87. Fantastic. Okay, we thus obtain vector x in terms of s and t is equal to vector y of s plus t times vector Darboux d of s. This completes the proof of theorem 87.3. Wow, double rainbow. Double rainbow indeed, man. Okay, last one, problem 87.3. Prove that if the rectifying developable surface is mapped isometrically in the plane, the corresponding curve becomes a straight line. Here we go. Short, sweet, and to the point. The proof, or the solution, is as follows. At any point of the curve, which has a vector parametric representation y in terms of arc length lowercase s, under consideration, the osculating plane is orthogonal to the rectifying plane. The normal vector to the rectifying developable surface capital R lies in the corresponding osculating plane of the vector y of s. In consequence of theorem 50.1, vector y of s, thus, is a geodesic on the rectifying developable surface capital R. Since the geodesic curvature of a curve is invariant under an isometric mapping, first we can refer back to theorem 57.2, vector y of s is mapped onto a geodesic in the image plane, that is, onto a straight line. Wow. Vector of Darboux. Incredible. That's the end of section 87. And I guess a little bit more foreshadowing. Section 88. I talked about this last time, but section 88 is on center surfaces of a surface. Maybe I didn't. Maybe I edited it out. But really, section 88 is all about a surface of Weingarten. Okay? Section 89, parallel surfaces. Really, it's just kind of a generalization of Bertrand curves. And then the finale, 91, 92, 93, 94, 95, 96, is all about constant curvature. And it's really like, you might as well start just getting deep into the weeds with Riemannian geometry. But we're not going to do that in this video. We're ending it right now. See you guys later. Peace.